Okay, let's get started with the problem number 10. And we're going to do 10 from 10 to 16 to the end of the homework. And it's chlorophyll absorbs blue light at, let's go, 460.0 nanometers. And emits so this is the wavelength of absorption. This is the wavelength of emission of chlorophyll, and it's 660 nanometer. Calculate the energy change. So this would be the energy, the delta energy, absorption and emission. Between absorption and emission, when a single photon, okay, of 460 nanometer radiation is absorbed and one of 660 nanometer is emitted. So basically what you have to do here is calculate the energy for each one, the energy of absorption of a photon, energy of lambda absorption of per photon, right? And the energy of emission, right, of a photon per photon too. And then you subtract one from the other one, right? And you calculate the difference in energy. Now, just let's write down the formulas on the right side here, and we know that speed of light is equal to the wavelength multiplied by the frequency. And we also know that the energy of a photon, Planck energy, is equal to the Planck constant multiplied by the frequency. Now, if we get, the first equation, we set it up in terms of frequency, right? We can plug it in on this equation, and it's going to be, when we divide everything by wavelength, both sides, and it gives you that the frequency is speed of light divided by the wavelength. So the energy of a photon would be equal to the Planck constant multiplied. Let's plug in right here the frequency. It's c over wavelength. Now, as you see, the energy is inversely proportional, and that's an important thing to remember. And to understand, it's inversely proportional to the wavelength. So that means that if you have a higher wavelength, the energy would be smaller. So that means that when the emission, the absorption energy, right, it's going to be higher than the emission. That means that the chlorophyll absorbs light energy. So how are we going to determine this difference? We are going to determine if its absorption is a positive sign, right, and it's the energy. Let me draw the E in a different energy of absorption minus energy of emission. Absorption is higher. As I said, the absorption is 460 and emits the light at 660. That means that and the wavelength is inversely proportional to the energy of the photon. So, by the way, this is, So let's find out first the energy of absorption. And it would be equal to, per photon, don't forget this always, per photon. And would be equal to Planck constant. What is the Planck constant? Always it's going to be given. It's 6.63 by 10 to the minus 34 joules multiplied by seconds. So 6, we plug in the Planck constant here in this equation, and it's 663 by 10 to the minus 34 joules multiplied by second, multiply, yeah, it's right, that constant, 663, and multiply by speed of light, that it's 3.00, the speed of light, let me write it down here too, speed of light is 3.00, that's the one where the homework is using, so that's the one we should use, and I'm using now, and it's by 10 to the 8th meter per second. Now, an important thing before we plug in, and don't forget, because I started to do it, and before we plug it in, the speed of light is always going to be given, in meter per second. If the speed of light is meter per second, before we start anything, any calculation and plug it in any value, we always have to just convert each wavelength from nanometer to meter, and it's 460 nanometer. To convert it to meter would be 460 point nanometer multiplied, because 1 meter is equal to 1 by 10 to the 9th nanometer. So the desired unit would be on top, 1 meter, and given on bottom. Okay, so that would cancel out nanometers and nanometers, and it's going to be 460 by 10 to the minus 9 meter, or which is going to be the same as 4 point in standard scientific notation by 10 to the minus 7 meter. Now, the same with the wavelength of emission, and it's the same conversion, so I'm just going to put the results, and it's going to be 6.60 by 10 to the minus 7 meters. Now, when we get into the energy, let's calculate now the energy. We have it in the same units as speed of light. And it's going to be 6.63 by 10 to the minus 34 joules multiplied by second by the speed of light. Okay, here look at the equation. Let me put it on a let me put it in a box. Okay, and it's gonna be the speed of light 3.00 by 10 to the 8th meter per second, and divided by the wavelength, which is gonna be 4.60, and this is the energy of absorption. Let's start with absorption, and let's plug in the lambda of absorption, which is going to be 460 by 10 to the minus 7 meter. You cancel out meter, and your final units are going to be 1 over second. Second and second are going to cancel out now here, and then your total unit of energy is going to be used. So this is going to give you, right, 432.32 by 10 to the minus 19 joules. Now, on the next step, we are going to calculate the energy of emission. And I'm just going to give you the value because it's the same math. You can do the math and verify the results. So it's going to be, you're going to do the same thing. Okay, you calculate the energy of emission, right? 3.01 by 10 to the minus 19 joules. And then the difference in energy would be equal to the energy of absorption minus the energy of emission. Now, why I chose this? Because the energy of absorption is higher than the energy of emission. And as it is absorbing, because it emits less energy than what absorbs. So that means that the chlorophyll is absorbing. So it's endo, positive sign. So it's going to be, you're going to subtract both of them. Just do the calculation and you should be able to get results. But it's 131. I'm going to give you on this problem, I'm going to give you the values. But generally what I'm going to do is do the setup and you do the calculation and get the results. Now let's go ahead, right? Under number 11. Number 11 on the homework, from the homework, and it's after the lowest frequency light that will produce the photoelectric effect on a material is called the threshold frequency. So the threshold frequency for platinum, PT, right? Okay, the lowest energy that would be absorbed and produce, the lowest energy that would be absorbed and will produce a photoelectric effect. So that means that for platinum to produce a photoelectric effect, at least it has to absorb, right? Energy absorbed, or a photon with energy, with a frequency. The energy absorbed will depend on this frequency. And this frequency is the minimum, and it's going to be 1.3 by 10, and this is a 15. 10 to the 15 second to the minus 1. Okay, let me explain it again, rephrase it. What it means is that the energy, that the frequency of light on the platinum, the minimum frequency that platinum have to absorb, okay, of energy. Okay, the energy, right, minimum energy that will produce, okay, a photoelectric effect and will emit a quantum of energy is going to be at a frequency of 1.3 by 10 to the 15 second to the minus 1. So that means that if platinum absorbs energy with a frequency, or light with a frequency lower than 1.3 by 10 to the minus 15, it wouldn't absorb enough energy to produce a photoelectric effect. So, and it depends in each material because it depends on the electron configuration. We saw it, and how the electron gets excited when it absorbs light. So basically, what do we have to do? What is the energy of a quantum of this radiation? This is very easy because what you have to do is, knowing the equation, right? Speed of light is equal to frequency, wavelength multiplied by frequency. Sorry, this is a frequency. Okay, and then we don't need that equation because it's so easy that we just have to plug in this. The energy, threshold energy, would be equal to the Planck constant multiplied by the frequency, and it's the threshold frequency. Okay, threshold frequency. So let's do something. Let me erase this because this is even easier. What you have to do is calculate the energy absorbed, the minimum energy absorbed to produce a photoelectric effect. And that would be using the minimum frequency, the threshold frequency. So that would be this value. So you plug in this value and you calculate this energy, and that should be the answer for this question. Let's go. Let me give you the value. Energy is equal to 8.6 by 10 to the minus 19. Just do the calculation and see if you got the same thing. Now on the part B, it's asking, right? Will platinum display the photoelectric effect when exposed to ultraviolet light? And the violet light has a wavelength around 100 nanometer. And what about infrared? So what is for ultraviolet, the wavelength is going to be around 100, but we're going to take 100, a good guess, because we need to use at least this number. And then we got IR, infrared, and the wavelength would be around approximately 1.00 by 10 to the minus 3 centimeter. Now be careful, this is centimeter, okay? So the first thing you have to do, again, you're going to start using this for these values for the energy formula. What are we going to do? And what's the first thing you're going to do? Okay, let's calculate right now what is the energy for the ultraviolet energy and compare it to the energy of platinum, which produces a photoelectric effect. If this energy of the ultraviolet light, it is higher than this energy, it will produce a photoelectric effect because this is the minimum need. If it's less than, the platinum would not display photoelectric effect. And photoelectric effect, remember the concept, is the energy emitted. That's it. Of an atom when the electrons are excited to a higher energy level by applying energy in the forms of light or electromagnetic radiation. So let's go ahead and the first thing we have to do is calculate the energy at 100, wavelength 100.0 nanometers. The ultraviolet, let's put here ultraviolet. By the way, we need to do the conversions to plug in the formula. And let me first let you know what you need to do here. And it's the energy, okay, of the ultraviolet. It would be a Planck constant multiply. And if we plug in from the problem number 10, if you remember that C equals to wavelength multiplied by frequency. If you plug in the frequency here, you plug it in so we don't have to calculate. Whatever it works better for you. But I like to plug it in directly. So the only thing you have to do here first is to convert. Don't forget, 100 nanometers. Again, it's 1 meter divided, remember, it's 2 meters, by 10 to the 9 nanometers. Nanometer and nanometer are gone, and it's going to be 1 by 10 to the minus 7 meter. Please check the calculations. And the same thing here is centimeter. Be careful because here, what I do is convert first to meter, even though if I have to go up and then down on the scale, on the conversion factors with System International. So 1 meter is 10 to the 9th nanometer. And 1 meter is equal to 100 centimeter. So what I start is converting to meter, and then I go back to nanometer. So it's 1 by 10 to the minus 3 to the minus 3 centimeter. Let's convert it to meter. And it's going to be 1 meter desired unit. Hold on. It's 1 meter. Okay, the opposite. We want to convert it. No, we don't need nanometer. I'm just complicating myself. No, we don't need a nanometer. We just need to convert it to meter, from the centimeter to meter. That's it. I'm sorry for that. And it would be 1 meter divided by 100 centimeter. That's it. Okay, the conversion factor. We cancel out centimeter, and it's going to be divided by 100. So it's going to be 1 by 10 to the minus 5 meters. Okay? I was going to complicate things. Now, the energy of ultraviolet, what you need to do is plug in. And so 6.63 by 10 to the minus 34, right? Joules multiplied by second, multiply speed of light by 10 to the 8th meter per second. And then you divide it by the wavelength in meter, 1 by 10 to the minus 7 meter. Now the energy for the IR would be the same, but with a different value of wavelength. 6.63 by 10 to the minus 34 joules per second by 3.00 by 10 to the 8th meter per second divided by 1 by 10 to the minus 7 meters. Cancel out, second and second cancel out, and you're left with joules. Now what is it we're gonna do with that energy? Well, if the energy of UV, okay, is you're applying a higher energy than the threshold, of course, the platinum is going to meet, how I said, a photoelectric effect. Once you get this number, you have to compare it to this one. If this is greater than this one, that means that, yes, it's a photoelectric effect. The same with this one. And if it's less, it won't be possible. So let's go ahead, and I think I need a little bit of space here. Hold on. Let's move this. And let's go ahead and look at the problem, the part C. Now, here, you can analyze each one, but I'll give you the concept, okay? The question is, let's go back to the question for a second. The question would be, what would happen in both cases if the original intensity of UV and IR and infrared light were double? Now, if you increase the intensity of the light or electromagnetic radiation, is increasing the energy. It does not increase the total energy, okay? I mean, the energy in total, but not energy per photon, which is going to be the same. And this, remember, this is per photon, and this is per photon. So what is going to happen? You increase the energy, right? Not the energy per photon. So you're going to have more photons. So you're going to increase the emission, if is that the case. Therefore, an increase of UV intensity will increase the photoelectric effect. If both have an increase, if both produce a photoelectric effect with platinum. Now, if the case IR or UV that you haven't looked at the results. If you need the result, just email me, and I will give them to you to double check. but the math is simple. The most important thing, you understand how to do it. And so if we increase the energy, right, but not the energy per photon, right, then what's going to happen? You have more photons absorbed. So you're going to have more photons emitted, right? And you're going to increase the intensity of the photoelectric effect if the light, either IR or UV, right, that you're going to determine on part B, produces the photoelectric effect. If one of these doesn't produce it, or UV or IR, then it has no effect. Okay? Now the part D. Part D asking if the wavelength of UV light decreases the energy. Okay, hold on. What happens if you decrease the wavelength of UV light use? What would happen if the wavelength of UV light use was decreased? What happened when you decrease the wavelength? Look at the energy formula. The energy is. That's why I like to use this formula like this. Look at the UV energy. So if you decrease the frequency, the energy is going to increase. But be careful. On part B is the energy per photon, what you're increasing on the total energy. So the increase of energy per photon. So if emits, right, if the UV, right, in the case of UV, produces a photoelectric effect, what is going to happen with the increase of energy per photon? You're not gonna go like letter C, that you're gonna emit a intense light. The photoelectric effect would increase because we're increasing the total number of the total energy or the total number of photons. In this case, we will increase the energy per photon. So what is going to happen? Well, in the case, if producing a photoelectric effect, what is going to happen is that energy absorbed, not emitted, absorbs, increase in energy per photon, is going to be converted to kinetic energy. That it's kinetic energy on the speed of the electron, the movement of the electron. So the electron is absorbing, remember the energy per photon. Photon is the minimum energy of an atom, of an electron, and minimum energy quantum energy. So if an electron absorbs that energy, that quantum, and that energy is increased, what is going to happen with that? Well, it has to be transformed, because it's not emitted. It's not increasing the total energy emitted. It's just increasing the energy per photon. So that would be transformed into the kinetic energy. So the electron would move at a higher speed. Let me move it a little bit up. And let's look at the number 12. Number 12, transform the Rydberg equation, okay, into the modified Bohr expression. What is the Rydberg equation? In general, Rydberg equation, it's expresses the 1 over the wavelength by a constant multiplied by 1 over the energy level 2 to the square, the initial, sorry, that's an I, minus 1 over the energy final square of the final, the square of the final energy level. So what did Bohr took it? He modified this Rydberg equation and took it to the energy level. So what do you have to do? You're just the energy level of an electron, and to the difference in energy between the energy levels of an electron. And if you have, okay, an electron, right, in an energy level of 1, for example, and then you have it on 5, what Bohr did is calculate the difference in energy between the two states. So what do you have to do? What you basically have to do is use, okay, use the 1 over lambda on energy. So you get here that the energy, right, Planck energy for a photon would be this, okay, multiplied by the frequency. But we did it already, and we said, well, energy is equal to Planck multiplied by the speed of light divided by lambda. And what happens is that if you plug in 1 over lambda, you would have, right, the difference in energy. Okay, let's just plug it in, sorry. Let's just plug in the value. Hold on, here, sorry. Let's plug in, okay, the value of energy, okay, and or 1 over lambda. So if you go ahead and make it 1 over wavelength, right? I divided by both sides by h and c, and I would have this. So the final energy minus the initial energy minus the final energy, the energy of a photon, the energy emitted of a photon electron going down to a lower energy level, it's going to be, right, it's going to be 1 over lambda. Let's take it and plug in this, okay, on the left side. And it's going to be the energy, right, from a final step energy from a final step divided by hc equals 1.09677 centimeters to the minus 1, okay, and 1 over n initial to the square minus 1 over n square, the square of n final. And this is per joule, without the joules. Now, without doing a great thing, this would be the same as the difference in energy, right, from initial to the final, right, because we're considering both state. So what we have to do is multiply h by c by 1.09677, and this is the same constant, right, 1 over n I squared minus n f squared. And this is meter per, this is, let's do the calculation. This is the only thing you have to do. That's it. And it's like h 6.6, and in 3 by 10 to the minus 34, right? Multiply by, and by the way, this is joules, right, per second. Multiply by C, 3.00 by 10 to the 8 meters per second, Because what Bohr did is use that equation, but what he did, and instead of wavelength, he calculate, or he got the equation, right? He represented the equation in terms of energy to find out the energy of an electron when it moves from the higher state, releases the energy, the photoelectric effect, and goes to the lower state of energy. So here you got this multiplied by 10 by 109,677 centimeter to the minus 1. But let's do something. Let's convert centimeter to the minus 1. And you know that this is 1 centimeter to the minus 1. 9677 1 over centimeter. And you know that 1 meter, right? It's 100 centimeter. And what do you want? You want on the bottom, the meter, okay, to cancel it out with the meter per second. So how do you do it? You would do it the opposite way because it's on the bottom. So you multiply this, so the desired unit has to be on bottom, and it's 1 meter, right? 100 centimeters. Right? And it's going to be centimeters and centimeters cancel out, and you would have 19677 by 10 to the second 1 over meter. Okay, what I did is convert it by 10 to the second, right? 1 over meter. And let me go to the right, but it's the same expression. This, I don't get into this because that's the same thing you're going to find on Bohr's expression. And it's 1 over the square of the final energy level. And if you calculate all this, right, it's going to give you a new constant. Hold on. Okay, here we are. So the energy, the transition energy from a higher energy level of an electron to the lowest one, you can represent it as it means the same to the final, would be this, right? And if you look at this, meter and meter would be canceled out. And what do you have here left? By the way, this is not, joules is not gone. It's an arrow on the line. Okay, this is joules. So your resulting equation should be, if you do all this calculation, it should give you 2.18 by 10 to the minus 18. And by the way, maybe a little bit off in some numbers. For example, the homework uses 6.625, but I don't want to change that because we already been using this. So maybe you got a little bit of different there when you do this calculation. Ni square minus 1 over Nf square. And this is in joules. Now let me get it on red here. Right? And let's look up here at what do we wanted to prove on this problem. It is the same, 2.179 by 10 to the minus 18. Just compare it and you'll see it's going to be the same. You see? 2.118 by 10 to the minus 18. The other one gave you if you look at your homework, okay, it's 2.179. Okay, perfect. Now before we go, let's stop here and I'll record a new video from the 13th to the 16th.